All right, 2.11 logarithmic functions.
Because logarithmic functions and exponential functions are inverse functions, the characteristics of their graphs will have inverse relationships.
Love it. Keep going.
Key characteristics of logarithmic functions. A logarithmic function has the general form f of x equals a log base b x. B is greater than 0, where a and b are constants with a not equal to 0 and b not equal to 1.
All right, fantastic. So I'm going to refer to this as the constant multiple, and I'm going to refer to this as the base of the logarithm. The base of the logarithm is always going to be greater than 0 in our cases, and a is going to be our coefficient of our logarithm. Now, our domain for our normal logarithm is going to be 0 to infinity. And the reason behind it, and so if you want to take notes, you're going to set whatever it is inside that logarithm greater than 0. So for instance, if we have like, let's say log base 2 of, I don't know, x minus 2. I'm going to take this x minus 2 and I'm going to set that greater than 0. And so then I'd have what? X is greater than 2. And so the domain of this one would be from 2 to infinity. All right, and so that's how we're going to work with that. Now, the range is going to be negative infinity to infinity on all of them. Now, this is what a common logarithm looks like. Okay, so logarithms are slow-moving functions, but they do increase. All right, so when your a is positive and your b is greater than 1, it's going to look like that. All right, and so when we have a negative out front, what does it do? It flips over the x-axis. So now we're going to have our logarithm look like that. All right, keep going. You're doing great.
Awesome. Logarithmic functions, a is greater than 0 and b is greater than 0. Looks like that.
All right. So now we're going to increasing versus decreasing.
Increasing versus decreasing. Logarithmic functions are always increasing or always decreasing. They will never switch from one to the other. So they have no relative parentheses local extrema unless on a closed interval.
All right, remember on a closed interval it has endpoints and we can't actually call them relatives in this class. All right, concavity.
Awesome. Concave up versus concave down. Logarithmic functions are always concave up or always concave down. They will never switch concavity, so they have no points of inflection.
All right, in behavior.
For logarithmic functions in general form, as the input values increase without bound, the output values will increase/decrease without bound. Since logarithmic functions have a restricted domain, they are vertically asymptotic to x equals 0. As a result, the left in behavior will occur as x approaches 0
All right.
to the right.
We're going to talk about that further. However, it's basically this inside part of our log. If we set that equal to 0, that will give our first asymptote. And so on this one, where would be our asymptote for log base 2 of x minus 2? It would be at what? At 2. X equals 2 would be our vertical asymptote, and we'll talk more about that. And so our in behavior is not just going from negative infinity to infinity, but it actually be 0 from the right. So if you look at this graph, does it actually go to negative infinity? No, because we can't actually evaluate a log of a negative. And so if we kind of just, let's just freestyle one. If we have like log base 2 of like, let's say negative 2, how would I solve a log? I'd set it equal to what? Like c, right? And so then I'd have a to the c equals b. So I'd have 2 to the power of c, which is equal to negative 2. Can I get any value of c to give me a negative? No. And so that's why it's usually from the right of 0, because I can't actually get a negative unless it's horizontally shifted. All right, cool. Keep moving. You're doing great.
Awesome. In behavior limit statements, the limit as x approaches 0 from the right, a log base b of x equals negative or positive infinity, and limit as x approaches infinity, a log base b of x equals positive or negative infinity.
All right, so example 1, we're going to talk about the in behavior of these logs. And so on f of x, the first one for our left-hand limit, we'd have a limit as x approaches 0 from that little plus sign. What does that little plus sign mean again? From the right. Okay, so I'm going to the right of 0, and so it's approaching that way. And so what's it going to? Negative infinity. And so how would I write my right-hand statement? I'd have a limit as x approaches what? Positive infinity of f of x. And so as I approach positive infinity, which means it goes to the right, where does it go? Positive infinity, exactly. All right, let's do on part B now. So on this one, to find my left-hand limit, it'd be a limit as x approaches what? 0 from the right again, of h of x. And what's it doing as I approach 0 from the right of h of x? It goes to positive infinity. And so then as I go to the right, this would be a limit as x approaches positive infinity of h of x is equal to what? Where's it going as I go right? It's going down to negative infinity. All right. Now on this one is where I actually like to sketch our little graph. All right. So I have a, which is positive. Okay, see how I have 2 log base 3? So a is positive, b is also positive. And so which way is it going? Is it kind of going up or is it kind of going down? So is it looking like an A or a B example? So does it look like this one or does it look like that one? It looks like the A example, all right? And so I would kind of quickly sketch a little graph that kind of looks like that, and that will kind of help us walk through this one. And so if I do a left hand, I'd have a limit as x approaches what? 0 from the right, all right, of g of x, which would be equal to what? Negative infinity. And then to write my right hand, I'd have a limit as x approaches 0 from the, oh, sorry, x does not approach 0, x approaches what? Infinity of g of x, which would be equal to positive infinity. All right, keep going.
Example 2, for each of the following, determine if the logarithmic function is increasing or decreasing and concave up or down.
All right, calling somebody.
10.
10, dang. Let's look at it, part A. Is this concave up or concave down? Concave up. Hold the water. Is it increasing or decreasing? Decreasing, going down. Calling somebody. Concave up, concave down.
Concave down.
Concave down. Increasing or decreasing?
Increasing.
Increasing. Very nice. All right, calling somebody.
Aiden.
Aiden. All right, so on this one, I have negative 4 log base 6 of x. So does it look like something like A or does it look like something like B? Looks like something like A. And so it's going to kind of look like that. I would quickly give it a sketch. And so is this concave up or concave down? Concave up. And then is it increasing or decreasing?
Decreasing.
It's decreasing. All right, let's keep moving. Here we go.
Example 3. Selected values of the several logarithmic functions are shown in the table below. For each table, find the value of the constant k.
All right, so let's talk about these logarithmic functions first of all. What do we know about logarithmics with tables? What do we know about input values? What are they doing?
They don't edit additively.
No. The input values are multiplying. All right. And so what do we know about the output values or the f of x or the y or whatever? What are the output values doing?
Additively.
They're doing additively. All right. They're adding from term to term. All right. And so that's what we need to know about logarithmic functions. So let's look at part x and f of x. So what's happening from my x's? They're multiplying by 2. And so because they're multiplying by 2, what do we know k is on this one? 4. All right, cool. Let's do another one. All right, and so make sure we have additively on g of x. So are we having equal gaps over here? Yeah. And so on this one, what's it doing? It's multiplying by what, Mary? 3. It's multiplying by 3. And so when it multiplies by 3, if I were to go backwards, k would equal what?
2.
Love it. All right, this next one. This next one's a little bit tricky because if you go 4 to 5 and 5 to 7 and whatnot, you don't really see the gaps. However, we kind of did these before. And so what were my gaps? What is my gap between 4 and 5? 1. And then what's my gap between 5 and 7? 2. And so what's happening? It says it's a logarithmic function, so they're being multiplied. And so what's happening from my gaps? They're being multiplied by what? 2. And so if my gaps are being multiplied by 2, what's my next gap? 4. And then my next gap would be what? 8. Okay, because they're being multiplied by 2. And so which one would k be then? It'd be 11, all right, because 7 plus 4 is 11. 11 plus 8 is also 19. And so k would equal 11 on that one. All right, see how we did that one? All right, fantastic. All right, Kyler, let's look at this next one. So now we have 7, 14, 21. So my outputs are linear, which is good. And so let's look at my inputs. So I go from k to the negative second, or e to the negative second, I'm sorry, to e. Well, what's it being multiplied by? Okay, what's it being multiplied from e to the 7th to the e to the 10th? And so, what are they being multiplied by?
E to the third.
E to the third. Okay, and so I'm multiplying. E to the third is just a number. All right, it's like 11 or something. I don't know what it is. No, it would be a lot more than that. All right, it's a number though. All right, and so now I multiply by e to the third. And so, what would that one be?
E to the fourth.
E to the fourth. All right, so now my k would equal e to the fourth. All right, cool. We're almost done. Example 4.
Find the domain and range of the following logarithmic functions.
All right, so I'm going to go a little further than what this is. However, we're going to do this obviously. All right, so domain. Remember, you have to do these input values. All right, and so you just set this x is what? Greater than 0. And so to find our domain, we're just setting that equal or greater than 0. And so what do we get? From 0 to infinity. All right. Now I'm going to graph it. I'm going to sketch its graph. Does this go up or does it go down? It goes up. Why does it go up?
Positive.
Because a is positive. My coefficient is positive. And so it goes up like that. Now, what is its range? Negative infinity to positive infinity. Now, I want to also go a little bit further. What's its vertical asymptote? It's whatever that is set equal to 0. And so, what do we get? My vertical asymptote would be x equals 0. So, basically that means when I cross its bound, oh, there it went. All right, so I can't actually get over there, or else I'm taking a log of a negative, and we can't do that. All right, let's look at part B now. And so let's start out with finding its domain. And so what do? We set x minus 3, what? Greater than 0. And so x is what? Greater than 3. And so what would be its domain then? 3 to infinity. All right. And so this is where I'm going to start sketching. All right. I know we don't actually need it for this one. However, I'm trying to lead you in. All right. And so what would be its vertical asymptote? X equals 3. All right. And so it's not crossing there. Now, is it going like what we did in part A, or is it going to flip? It's going to flip. All right, and so now it's kind of moving down like that. All right, and so again, what's its range? It's still what? Negative infinity to positive infinity. All right, let's do one more. And so we have 8 log base. What is this base, by the way? 10. All right, it's a common log of 2x plus 3. And so on this one, when we find its domain, we set our inside, which is 2x plus 3, which is greater than 0. And so how do we solve for x on this one? Subtract 3 and then divide by 2. So x is greater than what? Negative 3 halves. All right. So what's my interval? Negative 3 halves to infinity. All right. Now I want to do its little sketch. All right, and so negative 3 halves is over here. Now, which way is it going? Is it moving up or is it moving down? It's moving up. And so our logarithm is looking like that. I'm not talking about its x-intercept at this point in time. We'll go into that later. However, that's what it will look like. And so what would be my vertical asymptote again? at x equals -3/2. And so what would be its range? Negative infinity to positive infinity. All right, pretty good. Cool.